Back to the grind. So I want to, before we get moving forward on our schematic and our design and doing some actual wiring, I want to show you a couple tricks that could save you a lot of time and effort. So the first thing is Altium doesn't have the best built-in revision control. It does work well if you're willing to go through the process of setting it up. I'm rarely willing to go through the process of setting it up. They try to get the Vault, the Altium online content repository. I guess that does a pretty good job with it. I haven't used that much, where you set up your own kind of cloud repository for some of this stuff. But what I'm going to show you is the easy way, the simple way to really back up things. So sometimes it's possible to have a project bump into an error that you just can't resolve. So sometimes it's like, I just can't, there's something weird, wonky, a little squirrel in the system, you can't make it go away, and you have to revert to a previous version of your project. What I like to do is periodically back up the project in a really manual way. So if I go to the the folder with my project documents, so in this case it's this, I just saved my project to the default location, which was users, public documents, Altium projects. And I found my project folder, and I'm just going to right click it, and I'm just going to go like, or we can even, if you don't have 7-zip, just do send to compressed zip folder. Boom. So I just backed up my project. So that was easy, right? But now, even if I save a file and then after I realize I saved it, there was something corrupt about it or something like that, I can go back to this old saved one. Altium kind of does that. If you open up the file and you go to this history folder, that's sort of how Altium backs up this stuff too, is it basically periodically zips up the files here, the document files. So if you ever do have something go wrong like that and you didn't back it up, you can try to pull an old version out through here, and that can be one option. I want to show you something else. So let's say we have our project and it's all saved, and we close this project. Let me first of all clean everything up here. Let's say we close this project. Close Altium, close everything down. Then I'm going to open Altium back up. Eventually. Okay, now this is nice. When I open Altium back up, I have my board and my schematic all here waiting for me. No, you don't. The problem is these files show up, but these are free documents. So these are just leftover, dangly, disconnected documents. My project is not open right now. My project is not open, but the guts of my project are laying here bare. And the problem is, if I mess with these, it will change them. And if I save them, it will update them and change them in the project. But I haven't changed the actual project itself. So you never want to operate, you never want to modify your documents as free documents. You always want to, when you start up Altium, close all these stupid free documents and open your actual project up. So you want to go open project and then choose this project. And now we actually have the open project with those source documents as part of it. That's a big mistake students make. Sometimes students will go to a lot of effort making changes to documents, and the whole thing is messed up because they didn't make those changes in the context of their project. So any files that were created, any dependencies that were created, any preferences that were changed, any of those sorts of things that would have been saved as part of the actual project file are now gone. So, and any linked, any associated thing, if you generate other documents out of these, you generate design files, something like that, none of it will be linked with a project, and it'll be very difficult to come back from. So always, always, always be sure to, just because you see the file doesn't mean it's actually open as part of a project. Always go back and open it as a project. Okay, so now let's go back to our design. Let's add, before we start wiring, let's add one extra detail. Let's add the battery charger. Okay, so if we want to add the battery charger, first of all, let's look at the data sheet for the battery charger. So we can go to, if we go back to, I'm creating your assignment in real time as I do this. So if we go back to files and we go to data sheets, we can find the data sheet for the charge controller here. And looking through this, so this is the English version of it. This charge controller is actually there's a lot of companies, and basically what they do is they take these really cheap parts from China and they create an English language data sheet for them and they rebrand them as their own parts. So that's what this is. This is the rebranded English language data sheet. All somebody did was translate Mandarin to English, and they charged 10 times as much for the part. It's funny. So let's look at what this charge controller is doing. So we can I'm going to teach charge controllers a little bit right now as we're going through this. So the idea behind a charge controller is a simple battery charge controller is always powered by a voltage that's a higher voltage than the battery voltage. You can get charge controllers that don't need that, but they usually have to have some sort of DC to DC switching converter as part of them, and it's a much more complex charger. These simple ones, in this case, they're powered by 4.5 to 6.5 volts is the specification, which USB is great for that. USB is 5 volts. And they have this decoupling cap, so they have a 1 microfarad decoupling capacitor there. And they have one output that goes to the battery, and they have one output that goes to this program resistor. And the program resistor is used to set the maximum current that can flow into the battery. You want to be really careful that batteries, depending on the size of the battery, it's usually there's a limit to the maximum current flow that can flow into the battery. So, and usually the ratings for batteries are C ratings. So they're basically what fraction of the capacity of the battery can be provided in terms of current input and output. So in terms of, quite often if you have a 500 milliamp hour battery, which has a charge rating of 0.5 C, that means 500 milliamp hours is the capacity of the battery. 0.5 of 500 milliamps is 250 milliamps, so the maximum charge current would be 250 milliamps in that case. Very small batteries can have very small maximum charge current. So things like a watch, if you have like an electronic watch or something like that, they can have batteries in them that are like 30 to 80 milliamp hours, and sometimes their maximum current is like 10 milliamps. So a lot of times they're, very small currents into those batteries, and if you drive too much current in the battery, it's going to get hot and it's going to damage the battery. It's going to shorten its lifespan. So we use this program resistor to set the maximum current. And other than that, it's fairly straightforward. Battery connects to the battery terminal, ground connects to ground, VN connects to VN, and a decoupling capacitor. Should be noted, the charge curves for these batteries are almost always have 3 phases. They have the constant current phase. The constant current phase is basically the battery is driven at a constant current, and while the charger is driving at a constant current, it watches until the voltage across the battery reaches a certain voltage. Once the battery reaches that voltage, it switches to constant voltage mode. Constant voltage mode is where it maintains that voltage and it lets the current just die down to whatever it needs to die down to until the current reaches a small value. As soon as, if you're applying the constant maximum charging voltage to the battery and the current has died down to like 10 milliamps or something like that, usually that's how you can tell the battery is full. The battery is that capacity. And then usually charge controllers will switch into either a trickle charge or to a just turn off charge termination mode. Intelligent battery chargers will basically fully charge the battery, and they know it's not good for a battery usually to stay fully charged all the way to the brink. So sometimes they'll actually, once the battery's fully charged, they'll disconnect the battery, and they'll even let the battery self-discharge a little bit before they start charging again. You'll see that a lot. If you have a laptop and you keep it, like Lenovo does this a lot. You have a Lenovo laptop, it's plugged into the wall. Your battery will say 100%, and you leave it plugged in and you come back the next day and it says 98%. And you're like, how did the battery get down to 98%? It's plugged into the wall. Well, the Lenovo charge controller is deliberately not keeping the battery maxed out at 100%. It knows that's bad for the battery. So what it does is it lets the battery discharge down to about 95%, and then it starts charging it back up again. So these are not that smart. These are like the 5-cent battery chargers from China. They don't do that, but they still do the 3 phases of charge. They still do the constant current mode, constant voltage mode, and then charge termination when it's fully charged, when the battery's charged. Okay, so looking at this thing, let's see. Maximum current's 800 milliamps. We're not going to go there. I don't really know what batteries we're going to use yet, but they'll probably be on the order of like 200 milliamp hour batteries. So to be safe, let's not charge these with more than 100 milliamps. So that means it's going to take 2 hours to charge the battery, but you'll live. It'll be okay. So if we're going to charge these with 100 milliamps of current, we have to find out, first of all, what program resistor we need to specify don't go more than 100 milliamps of current. So if we look down here at the oops. Trying to go through these curves, see the one I'm looking for. Maybe I missed it. Oops. What did I do? I'm not seeing it. All right, scroll down further. Oh, here we go. Formula, R program equals 1,000 divided by the battery current. That's easy. But what's going on here? Oh, this is if battery current is less than 15.1, less than 150 milliamps, which is us. We're there. So if we're looking for 100 milliamps of battery current, that's going to be 1,000. I don't need a calculator for this. I shouldn't. Divided by 0.1. That's 10,000. Sometimes you go for the calculator too soon. All right, so 1,000 divided by 0.1 amps. We're going to need a 10K resistor here. And look at that. They had that example already. All right, so we know, that looking at the data sheet, we know we're going to need a 10K resistor to program the current. There's another feature of these that wasn't shown here. So this charge status indicator. There's a pin, the charge status indicator. So it pulls down strong. It pulls down 10 milliamps of current when it's charging, and it pulls down 20 microamps of current when it's done charging. And so we can use this as a charging indicator. We can put an LED connected to this charge status pin to where when the pin pulls down the lower side of that LED, it will illuminate the LED for while it's charging, and then as soon as it's done charging, it'll turn off the LED, or it'll go to a weak. 20 microamps should maybe be visible, but it'll be barely visible in an LED. So it gives us a nice little tool where we can have a charge status indicator that shows that the device is charging. Okay, that's about all that I wanted to talk about. Yeah, and I mean, you can read through the data sheet. It's good. We're not going to spend too much time looking at those. So let's go back to our components. And if we lost our components, we'd go back. We'd go through that process again of, we could go back to the file-based library preferences, load the libraries we're looking for. So let's go to 320 part schematic library. And we have battery charger, LiPo charge controller. Top Power ASIC. That's an Asian brand right there, Top Power. So we're going to right click, place LiPo charge, and we'll put that here-ish. Notice this was labeled a U. U is the default prefix for oh my gosh. Oh, this is embarrassing. Embedded oh my gosh, I'm losing it. word slipped my mind. Oh, that's weird. That's scary. Maybe I'm going crazy. I'm definitely going crazy. Okay. All right. So we have our LiPo charge controller. VCC needs to be connected to. It's going to be powered by our USB. We could just run this wire. We could just run a wire across here, or we could just label it. If we want to keep it clean and not run wires across everything, we could just click the power port label, drop one, hit escape, double click the name, and just call it VUSB. Now, labeling this VUSB and this VUSB is exactly the same as having a wire across there. As far as the software is concerned, it's the same thing. These are the same net. Now we want to connect a program resistor. We want to add a 10K resistor between program pin and ground. Let's connect the ground up here too. So we're going to go to our components. We're going to go back to the miscellaneous devices. We're going to go to our old friend Res3, and we're going to scroll down and make sure, it keeps going back, we're going to make sure that 0603 is selected, and then we're going to right click, go place Res3, put that here, hit escape. We're going to place a ground on that one. And we're going to draw a wire. Escape. So escape cancels out of what you're doing. Tab usually sets preferences. So if I click on that and I hit tab, well, that's embarrassing. Tab used to do that. I don't know. I don't know what's happening. Why do they change things? I don't like change. They're changing it on me. Double click it, I guess. 10K. And again, changing the name here, changing it from 10K to 1K, it doesn't change the way it doesn't change the way our PCB is actually designed. It just gives us, it just tells us later on this needs to be a 10K resistor. Okay, now here's about connecting the battery. The battery is these batteries are fairly big lithium polymer cell with little wires coming off of them. Usually we have to have a way to make a connection to it. That's usually where we're going to use a through-hole connector. So typically we're going to use a port that lets us solder wires to it. I already had one. Remember when I had done this little 2-pin header here? So I can just use this as my battery connector. So the output of the charge controller is going to go to the positive terminal of the battery, and the ground is going to go to the negative terminal of the battery. So let's just call one of these negative, one of these ground, and the other one will just be the battery. So what does this mean? This means that physically, once I actually solder a battery to this header, this pin will be going into the positive terminal of the battery, and the other side of the battery will be connected to ground, which is what they said we should do in this, right? Right. Battery, one side of the battery grounded, one side of the battery connected to the battery input. Program resistor. So yeah, that's what we're gonna have to do. Let's put a status light. Let's put a status light in here. So it said that this charge pin pulls down 20 or 10 milliamps when it's charging and 20 microamps when it's done charging. I never trust those things. So theoretically, if that's true, we could just put a resistor directly between VCC and the charge pin. But I don't believe it. I don't believe it for 1 second that it's actually going to only draw that. So I'm going to put a resistor in series with this LED to make sure it's not damaged. So I'm going to go to components, and I'm going to go back to our 320 parts. And we have some options with LEDs. So we can do a surface mount LED, or we can do a through-hole LED. I don't personally care which one you pick. So we have an LED 3mm here, which is the through-hole one, and I think we also have an LED. Yeah, this says red. This says LED red, but you know, the color is whatever you pick, right? I mean, it's the same. It's an 0603 LED. Let's for now, yeah, let's do a surface mount LED. I want to do a surface mount LED for the charge indicator. So so the other LEDs I'll do through-hole. For this one, I'm going to do a charge indicator. So I'm going to right-click it, place it. Now, the charge pin is charged with a bar over it. Charged with a bar over it, if you from digital circuits, you know that means not charge. It basically means when you're charging, this signal's a 0. When you're not charging, it's a 1. So this thing pulls the signal down to 0 when it's charging, which means that the LED is going to have to be facing this way. So that charge pin is going to pull the signal down when it's 0. And again, I said I wanted to put a resistor in here to limit the current. So here's what we can do. When we already have a part out, I don't want to go back and find a new resistor. I don't want to do that. So one thing I can do is, I've already got a resistor here. It's still set as a resistor question mark. If it's a numbered resistor, sometimes doing this technique will mess you up. But this is just an unknown R question mark resistor. One thing I can do is I can hold down shift. If I hold down shift and I click that part, it makes a duplicate of it. So that was an easy way of just doing that. Another thing to keep in mind, if you hold down control and move a part, it takes the wire with it. So if I just grab this part and move it, it just runs away with it. If I hold down control and move the part, it moves all of the wiring it keeps the wiring connections all there. So shift and moving a part duplicates it. Control and moving a part keeps the wires connected. Just moving the part just grabs the part and pulls it away from everything. So if I'm limiting current to my LED, let's say I want to limit this to 5 milliamps current max, just to be safe. So, and just ballpark, if it's 5 volts across it, 5 volts from the USB bus, 5 milliamps, we want probably a 1K resistor, just ballpark. Yeah, it's not actually accurate. It's because there's forward voltage drop across the LED, but whatever. 1K is good enough, which means we're just going to call this a 1K resistor. Let's wire this to the charge, and then the other one. Now, to grab this VUSB, again, I'm just going to hold down shift, grab the VUSB, boop, duplicated it. So now I've got, when this thing is charging, when the USB is plugged in and this thing is charging, the charge indicator is going to pull down this signal. It's going to turn this LED on. As soon as it's done charging, it's going to only draw 20 microamps, which probably is not going to be visible in the LED. And of course, when the USB is unplugged, there's going to be nothing because it's powered by the USB. So, and I think this is good. Nope, it's not good. We're not done yet. We need to have a capacitor here. We need to put a capacitor. It's specified a 1 microfarad capacitor at the input. So let's do that. So let's go to the Explorer. Oops, components. Let's go to our miscellaneous devices. Let's go to cap semi is I think what we're looking for. Cap semi, and again, we want to go to 0603. Now this is interesting. Look at this part number. It says 1608, and then in brackets 0603. What does that mean when you see two numbers? Whenever you see two numbers, that's metric and imperial units. The metric is always going to be the bigger one. The imperial is going to be the smaller one. So this is basically saying this part is 0603, which means it's 6/100ths of an inch by 3/100ths of an inch, which is also that's also 0.16 millimeters by 0.08. Sorry, that's also 1.6 millimeters by 0.8 millimeters. So 1608 metric, 1.6 millimeters by 0.8 millimeters. 0603, 6/1000ths of an inch by 3/1000ths of an inch. So I think 6/1000ths of an inch. No, 6/100ths of an inch it must be. Sorry. Yeah, sorry, 6/100ths of an inch. I'm sorry. Yeah, of course, 6/1000ths of an inch. I think the previous video I said it was 6/1000ths of an inch. Sorry, 6/100ths of an inch. Yeah. 6/1000ths of an inch would be a very skinny part. They sell them though. They sell resistors that small. And it's something to note. A lot of students accidentally, some students will buy 0603 components, not realizing they're 0603 metric. Those are very small. 0603 metric is 0.6 by 0.3 millimeters, right? That is like grain of sand size, but they exist and robots can do it, but good luck to you if you try to do that by hand. Okay, spent enough time. We selected the 0603 version cap semi, right click, place cap semi. What's this going to be? This is going to be a ceramic capacitor. We don't talk too much about capacitor technology here, but ceramics are the bread and butter of surface mount component capacitors. Here's the thing though, if I want to fit this in here, it's going to be a mess, right? If I want to put this capacitor in here, it's going to it's going to start to get ugly because I already drew this thing here. Maybe I could have done this part better, but I didn't. So here's what I'm going to do. I'm going to move this over a little bit. I'm going to take all of this. I'm just left mousing right now. Put this cap back here, and I'm just going to do this. I'm going to hold down Shift, grab a ground, hold down VUSB, grab this, and I'm just going to leave this as is. So this capacitor now is a capacitor between VUSB and ground, which is for the LiPo charge controller. But I didn't label it as connected to the LiPo charge controller. I just said this is a capacitor between VUSB and ground. So if I play this game with this capacitor, I need to keep in mind this has to be part of the charge controller. And one thing I could do, let me just hold down Control, move this guy in to keep this guy a little tighter. Sometimes what you can do, if you're trying to keep things nice and tidy, is you can place a place a line. Sometimes what you can do is put a box around stuff sometimes. Hit escape to cancel, place text string. Isn't that nice? Right, look at that. Now it's very clear. It's very easy to see. Okay, this stuff is associated with this. Okay, so I think we're pretty much good then with this LiPo charge controller here. So now let's go through the steps. We've created this. Let's go through the design. Tools, annotation. So we could do the annotate schematic, but we can also do annotate schematics quietly. This is a feature that they added, I think, around version like 18 of the software or 19 of the software. It lets you annotate without going through all that change order stuff. So we're just going to do that. Annotate schematics quietly. And it says, you got 5 things you're doing. Proceed? Yeah, proceed. Okay, now we're going to do design, update PCB document. And there's no update quietly as far as I know. So, and we can review this. We can see what it's doing. Everything looks to be as far as I know. Okay, so we're going to execute changes. And it's good to keep in mind, sometimes it can't execute a change. Sometimes there's an issue. Can't execute a change. So now we've got all these parts here. A lot of times I like to keep things neat and tidy as I'm going along. So sometimes what I'll do is I will find similar objects. I just clicked on the designator and do this the same. And I'm only going to look at I'm only going to grab the designators that are too big. So I'm only going to grab the designators that are 60 mil high. And I'm going to select all of those designators, and I'm just right now going to change these to 30 mil. And then 6 mil, just to shrink our designator size. And I think there's a default that we can change that does that automatically, but just to get it out of the way. Okay, now so we have our USB-C connector. We have the resistors for that specify that yes, there's a device, yes, it can draw current. Now let's start piecing this charge controller together. A lot of students, when they're doing the board design, they just go by air wires. They just say, okay, this wire is connected between here and here. Okay, so I want to move this like here. And then they'll say, okay, this capacitor is between here and here, so I'm going to do this here. And I always tell students, go back to the schematic. See what these things actually, it can be very hard to see what R3 was and C1 is when you're not looking at the schematic. So I might say, okay, C1 was that input capacitor. So you know what? Maybe I just want C1 like kind of here-ish. Like maybe I just want C1 like near the USB connector where it's going to be getting power. And then what was, oops, sorry. And then what was R4? I don't remember what R4 was. That's the program resistor. Okay, well, I probably want that next to the actual program pin. There, something like that. And sometimes I want to flip this whole part around. So this pin is the VUSB pin is down here, but my VUSB on this part, just because I know, is sort of up here. Well, I guess we got two of them. But I'm going to try to keep the ground on the bottom. And I'm going to try to keep the VUSB on the top. So I'm going to flip this one. So ground is on the bottom, VUSB is on the top. And I'm going to take this part and I'm going to maybe flip it. Because I can. Now you'll notice this dot now. The dot is the pin 1 indicator. So the dot is that's a silkscreen part. If we switch to 3D view by hitting the 3 button, that will show up on the finished silkscreen. And that tells us what orientation. It's pretty easy to tell because this is a 5-pin chip. But if this had been a 6-pin chip, we might not have been able to tell where pin 1 goes if we didn't have that indicator there on the board. Okay, this is all looking pretty good. Let's see where. And again, I'm not trying to keep everything. I don't want things to be too tight. What was R4? Oh, R4 was that program indicator. See, looking at these air wires, they're crossing each other. So a lot of times I'll just rotate them, right? Just get them rotated. DS1 and R3. This was the charge indicator. You know, I want my charge indicator to be right next to the USB plug. When I plug that USB in, I want to see a light next to the USB turn on to tell me I'm charging it. So ultimately, I want to move this LED over here. So let's put it. Maybe I'll put it on this side of the charge indicator. Oh, jeez. Maybe I'll put it on this side. So I'm gonna, and I'll keep it kind of tight, right? I kind of want it to be next to there. So I'm gonna hit this designator. That's it. Sometimes when you click something, it clicks the wrong thing, and in Altium you can usually keep clicking until it chooses the right thing. If I were trying to get P1, and sometimes it'll pop this up. If you click something and Altium's like, I don't know what you're trying to click, you can choose which one you were trying to click there. So I'll move the DS1 label, I don't know, like here. Let's move the resistor for that next to it also. Nope, which resistor was it? Was it R3? Looks like it was R3. Okay. There's no rush. There's no need to keep everything squished up. I can hit the space bar and rotate it. P1 pin can stay there to tell me my USB connector. Grab that and move it. I can rotate that too. Yeah, we'll keep. Yeah, whatever. So the reason I'm putting these on the side is because I might want to make the edge of my board right here. If I make the edge of my board right here, then I don't want to have just text sort of filling it up. So if I want to keep the edge of the board tight, I can do it like that. And if this is the edge of my board here, I could move these components down closer to here. That's an option. The other thing is I can also move these to above the USB. I'll just move them above the USB. So I'll move these up here. How about that? So then we can keep this side. We can keep this side all nice and perfect. And I don't want to get these too close because this is a physical connector. If we hit the 3D view, we're getting close up to the edge here. If I was trying to get a soldering iron in here, it might be a little difficult. So maybe I'll move these even a little bit. Yes. Why push it? Why push it? Okay, how are we looking now? Looks pretty good. Looks pretty good. Yeah. Actually, this net R4 ground. Just put it like this. Okay. Okay. Do we have? Oh yeah, we got the charge. Okay, now, so this is where the battery is going to physically solder into. So the battery is going to physically solder into this, and one issue is I don't necessarily know which is ground and which is power after this board is made. There's no label. This is just labeled P2. We could know that the square pin is power or ground or something, but it might be nice if we give ourselves a visual indicator that this is which side is the positive, which side is the ground. So let's just place some text on here. So what we're going to do is we're going to change the layer that we're working on. We're going to hit this button. We're going to change the layer we're working on. We got to go kind of far because we have a lot of layers. To top overlay. So top overlay, this is that silk screen layer, that top silk screen of text that we can see from the top of the board. And then I'm going to go place string. And if I hit the tab button, it'll take me to the preferences for this. And I'm just going to change this to a plus. And I'm going to place it here. And then I'm going to hit tab again, change it to a minus. And look at that. Okay. So now if I'm looking at this board, if after this board comes back from the fab and I look at 3D view, I say, positive side of the battery has to go here, the negative side of the battery has to go here. Perfect. Okay. So I hit the 3 key to switch to 3D view, I hit the 2 key to switch back, in case that wasn't clear. Okay, let's start wiring this thing up. I always like to build my circuit in pieces. So if I have a piece of a circuit and I know there's not a bunch of weird other stuff connecting to it, I'll just start building it from there. I'll start piecing it together. So right now I can start piecing this thing together. So because this is not, this is USB input to the charge. That's one system, and then the battery to the boost to the everything else is going to be another part. So this is kind of isolated. So let's start wiring it up. So how are we going to wire this? So we can run wires on either the top or the bottom of the board. I can select layer 1 down here, and that's going to give me the top copper layer. Then what I can do is I can go up to this, which is the interactively route connections, and I can click it. And then it's telling me basically to choose a signal. Well, for now, maybe I'll choose these grounds. Let's get the grounds taken care of. So this pin is ground, and why are these pins around here ground? These pins around here ground because we connected the shield of the USB connector to ground. So with these things being ground, I can, after I click this, it kind of gave me a wire, and look what happens. If I try to move this wire through a signal that it's not supposed to touch, it avoids it, right? It's like, it's not gonna, this is part of design, electronic design automation, is the software knows, hey, you shouldn't be connecting that ground pin to that VUSB pin. Those are not electrically connected. You better not touch it. And so it helps us out. It doesn't let us just make a connection there. But it doesn't always know what we're doing. So in this case, ground signals are usually they carry a lot of current. The ground signal tends to carry more current than any other signal on the board, while possibly the supply carries as much too. So usually we want it to be a little fatter than that. These wires are looking a little spindly here. So if we want to make a fatter wire, we're going to hit the tab key. And that brings up the properties for the wire. And the width here, the width is set to 10 mil. 10 mil, that is 10,000ths of an inch. So right now these wires are 1/100th of an inch wide. That's not that wide. It's probably fine. That would probably actually work for this project because it's not a huge amount of current flowing through the circuit. But we don't have to use 10 mil for this. We have plenty of space right now. Let's bump this thing up to like, I don't know, to like 25 mil. Let's make it an even 30 mil. 30 mil. And look at that. Look at that. Much better. So we're going to make a connection here. We're going to click it. And then we're going to click this one. And might as well click this one. And click this one. And click this one. Now, here's the thing. I can route these. Actually, I can route these grounds like this. If I do this, it's going to route. It's going to connect all of those grounds together. And that's fine. There's an issue though when you have copper this thick. Copper is a great electrical conductor. It's also a great thermal conductor, which isn't always a good thing. Because sometimes if you have a really good thermal conductor, if you're connecting a soldering iron to the backside of this resistor here and you're trying to get it to melt the solder, it's going to be tough because this copper wire is going to be sucking all the heat away from the solder joint. So it's going to be keeping the solder solid. This is usually where you add what's called thermal relief. So thermal relief is usually this term for if you have a very short section of narrow copper before you make contact to a pad, then that short section of narrow copper is still fairly low resistance, but it has a fairly high thermal resistance. So thermal relief is is where you maintain good electrical resistance, but low electrical resistance, but high thermal resistance. So typically that's by having a short, narrow section of copper. So we can do that. If we wanted to actually do that properly, we can go back. So one thing, every time you click, it kind of sort of affirms it kind of sort of commits you to it, but not really. I'm just going to run this ground here and then double click and then hit escape. And I was clicking too much, so it left me this little squirrely thing here. So if I'm still in wire routing mode, so if I hit escape again, it gets me out. And I can select this little piece of the wire, and then I can move that up. So just to clean that up, I can move that back up. And then each one of these, I can go back to wiring, and I can do, see, that's too fat. We're not going to get good thermal relief there. So I'm going to hit tab, I'm going to cut it back down to 10 mil. Hit escape. Oops. Yeah. Sometimes Altium likes to help, and it doesn't help. So what Altium just saw, oh, the only thing you have connected is this pad. This extra piece of copper, as far as Altium was concerned, was just leftover extra. So it helped us and got rid of it. So if we don't want it to do that, go back to wiring. Wire this ground. And that's going to just trim it a little bit. Wire this ground. And then hit escape. Okay, so that's looking pretty good. Now, what if we had not wanted to wire this ground on the top? What if we'd wanted to wire it on the bottom? We could delete this, click it, and hit delete. If we wanted to run this ground connection between one side of the USB to the other on the bottom, all we have to do is click bottom layer, click wire route, and then boop. It's going to route that in bottom copper. So this is a copper trace on the bottom. So if we hit 3 and go to 3D view, I zoom out, and then I rotate this around. So to rotate, I'm holding shift. It brings up my little rotate ball. Then I right click and I whip that thing around. Now look at that, right? I can see, you can kind of see through the board. You can kind of see the copper on the top. It's a little transparent. But you can see this very clear copper on this side, right? That's copper running on the bottom of the board. And then the rest, this is copper running on the top side of the board. So that's all we have to do. Okay, let's connect some other stuff here. Let's connect these two VUSBs together. So, yeah. So right now I'm set to bottom layer, and that's why it's not letting me click this. Well, I guess it did. I click it and it switches back. So there's a couple things. I'm going to escape out of this. I didn't like that. But another thing you can do is you can hit the plus and minus button to shift between layers. So if you're set to top layer and you want to go to bottom layer, I'm going to hit the plus key, switches me to bottom layer. Hit the minus key, switches me back to the top layer. So I'm going to do this again and hit it. But you see what happened here? My trace is now fatter than my pin. So the trace kind of sticks out the side of the pin. I don't like that, because what's going to happen is that's going to make the copper distance between these two adjacent pins too close. There's no reason to make them too close. There's no reason to have it be bigger than that. So I'm going to hit tab. I'm going to make it a little bit smaller. We'll just call it 24 mil. All right, so make it a little smaller just so we're not getting too big for our trace here. Now you see, as I'm doing this, it's snapping to grid. But when I finished, I double-clicked, by the way. I double-clicked when I finished, and that completed the route. So as you're clicking, every time you click, basically it says, okay, this old route stuff, we're pretty sure that's what you want. We're going to firm that up. But this new stuff, we're going to let it be. Every time you click, it kind of adds a layer of certainty to the route you were trying to do. So I just double-clicked at the end to make sure that it finished routing all the way up to the pin. I'm still in routing mode, as I can see from this green crosshair, but I can hit the escape key to pop out of that. Okay, this is looking good. This is looking nice and clean. Let's connect this net here. So, yeah, and this is a little too fat. There's not a lot of current flowing on these traces. And so, if this is just a signal trace going through a 5K resistor. So, in this case, I might just I might make my trace thinner just for thermal relief. So I'm just gonna do 10 mil. There's no reason to go down to 6 mil. I don't think there's any reason to go down to 6 mil anywhere on this board. 6 mil is the limit for the fab. The cheap fabs don't like you to go less than 6 mil. And notice as I'm doing this, it's making nice little right angle turns here. That doesn't have to be the case. So if as I'm routing, I click this. So see, it made a nice little right angle there. If I hit spacebar, it's going to change the routing style. So spacebar did that. Spacebar again, change it to inside. Oops. Sorry, if I hit shift spacebar, hold down shift, hit spacebar. Now look at that. Now we got 90-degree angles. We got 90-degree radiuses. We have arbitrary. I don't like that one. Arbitrary radius. We have 45. I like 45s. 45s are nice. And then we have 45 angle. Not necessary. So 45 angle is what I like. This one was that capacitor. This one actually, this capacitor is, maybe I didn't want to do that actually. Usually these capacitors, you want to keep them fairly close to your input to your system. So I think actually I want to, I'm gonna delete this. I'm gonna move this and move this. I'm going to move this one over here and delete this little stub. And yeah, just decoupling capacitors, you generally, as a general rule, just keep them close. So, and then if we want, we can, oops, a little stub there we had left. If we want, we can, oh, it's not liking that. We can move that over, and then we can actually tighten up this entire thing if we want. Okay, and we'll deal with this kind of later. I'm not sure where we're going to put that yet. We'll find a place. Okay, so let's extend it out here. Do a little route. That's too fat. Too fat. That's better. But then this one, there's gonna be a lot of current flowing through here. So for VUSB, let's keep this kind of fat, this route here. Keep it kind of fat. Right up until the end, and then we'll change this to 10 mil. Just do the rest, just for a little thermal relief. Yeah, fine. And then we'll go back to routing. We'll route this one. Hit escape to get out of routing. We got to figure out what to do with this one now. I might just do it kind of sideways like this. Right, the bottom of these connectors are here, so my board edge can't be anything less than this. It's not great, but it's fine. So we'll just route this one. Beautiful. Not beautiful, but it's fine. It's fine. What about the ground over here? What about the battery ground? That's a good question. You know, let's just use the other side of the board. We got, let's use the other side. We got a through hole here, we got a through hole here. Let's just give it a nice fat pipe from one side of the board to the other. So let's switch to layer 2. Let's route. Go from ground. Look at that. Yeah. Yes. Okay, look at that. Nice. Now you notice that my resistor is now hidden, right? That's because I have layer 2 selected. I gotta get out of routing mode. That's because I have layer 2 selected. If I go back to layer 1 selected, it'll show that guy again. Okay, let's give it a ground over here. That's too much, too much. And again, this wire is thin. This wire is too thin to carry a lot of current a long distance, but it's not going a long distance. It's going to be, you know, ballpark 100 milliamps at most. Not even that in this case. Just basically whatever current goes to the LED. So it's not very thick. It's not good for carrying power a long distance, but it's not going a long distance. It's going short. This one was going a longer distance, but that's why I gave it a nice fat pipe. We got a freeway over here, a little side street over here. That's fine. And then this is my battery. This is my current going to my battery. And again, it's only 100 milliamps, so it's probably fine. But let's just stub it out and then hit tab and bust it up to our 30 mil. Type 30, it knows that it's mils. Yep. Okay. Yeah, that's not quite enough thermal relief. So I'm gonna just. There we go. There we go. Okay. All right. Now, what about this one? What's going on here? What are you doing to me here? What you doing to me here? All right. So we got to get this signal, which is pulling down that LED. We got to get it over to here. I don't like all these air wires crossing, so I might just move some stuff around here. Just play some games. Kind of, it's really more art than science here at this point. So looks good. Now our LED is going to be a little further away from our USB. Do I want to do that? No, I want this LED to be really close to the USB. I want it to be really close to the board edge, like that. So, you know what? That'll be fine. Let's move these designators. Let's make them clear. Oh, that's wrong. That's DS1, that's R3. And I think I can route this. Now I'm gonna do something fun here. So I can route the VUSB. And I can just and I can route this too. Whoa. Whoa. Now I'm kind of snapping a little. I don't like how tight it's snapping here, so I can hit G and change my grid. And I might want to change my grid to like, I don't know what it's at now, but maybe 10 mil. That's a little better. No, I'll do 5 mil. Yeah, I just want to kind of get this sort of balanced here a little bit. Yeah, that looks good. That looks good. Okay, now we got to route this one. You know what? Maybe I want to hit my grid and go back to whatever I was at, 25 mil. What was I at before? 0.1 millimeter? Nope. 20 mil? I don't know. Maybe 10 mil. Let's just stick it at 10 mil. It's fine. Now, I don't want to get too close. The software is letting me get to within 6 mil of this pad, but why, right? Like, why? Like, give it some space. Keep it spaced out a little bit. I do like to keep my conductors a little tight, you know, when it's, when it's not necessary to have them be, that close is good. It doesn't have to be too close though, right? Or, yeah, not too close. Now what I'm going to do, I'm going to route this down through the middle here like that. I'm going right through the middle of the part. What are we doing? Yeah, see what I just did there? Snuck that signal in. Now look, I haven't had to use any vias yet. I haven't had to use any vias or vias, however you want to pronounce them. A via or via is, depending on if you're French or not, is how you make a connection of a trace between one side of the board and the other. So quite often, if you have a signal that has to get from one part to another part, it's got to cross a bunch of conductors that are on the same layer as it. it makes sense to just pop it down to the bottom layer, route it down through the bottom, and then pop it back up. And so if you're doing that, you need to use a via or via. And we haven't had to use them yet. So we were able to route this entire section without using one. That's great. So that is super. So we're going to call this routing. This looks pretty good. I mean, I'm pretty happy with this. I'm going to hit escape. There's a couple things I want to do. I want to clean up my annotations. I want to clean up my markings. So clearly my grid was not set to 20 mil before, because it was not set to 5 mil before. Well, maybe it was. Clean these up a little bit. U1 is this chip. R4 was this one. We just want to get these close. We just want to get these close enough that when we're assembling this, we know what's what. And this P1 is bothering me a little bit. Let's move it here. Now, it's a little disconcerting at first to say I'm dragging this label over the wire. Kind of looks a little strange, but after a while, you get used to the fact that in your head, you get used to that, to the reality that the silkscreen can cross wires. It can't cross pads, but it can cross wires. So if we hit 3 and go back to here, look at how nice this looks, right? Everything looks pretty good. We have our labels here. I might move that U1 label down to the bottom, just like that. Now, I always like to go back. And is it clear that U1 is this and R4 is this? Yeah, it's pretty clear what part's what. Also, it's pretty obvious that this is not a integrated circuit. Jeez, U is the designator for an integrated circuit. So it's pretty clear that this is not an integrated circuit, and this is. So I think it's looking pretty good. I'm pretty happy with this so far. Okay, so let's call that a good chunk. But I want to do a couple things before we leave right now. So before we get going, I want to show you. First of all, save. Oh my goodness, save all. I also want to show you some other techniques we can do. So I always like to check everything over, make sure it looks good, go into the 3D view, make sure it looks good. It's fine. This is all fine. There's a couple tweaks I might make if I cared more, but I think this is good. There's ways that we can use this software to help catch errors. And it's not foolproof. It's not like it checks for everything, make sure all of our problems go away. But one thing we can do is we can do what's called the design rule check. So built into the software, we have a bunch of rules. Rules that say 2 pieces of copper, if they're not the same signal, can't be within 6 mil of each other. Rules that say your parts can't be more than 14 mils from the edge of the board. Rules that say the smallest hole you can drill is 13 mil. You know, things like that. These are rules that the software knows the fabrication facility you're using can't go beyond these. And these, for this software, because you loaded the preferences from the WWU preferences file, those are built in. Those default fabrication preferences are all built in. So it should work, as long as it clears the rule check, it should not get rejected by the fab. But the rule check is a really good way to make sure we don't have any problem. So let's run the rule check. So just tools, after we've saved, we go tools, design rule check. And run design rule check. And, oh no, 16 rule violations. Don't worry, there's always some rule violations, but where they are matters. Do we have unrouted nets? No, good. Do we have clearance? No, good. Do we have short circuits? No, perfect. Hole constraint. These are the critical ones. What's the error that we have? Silk to solder mask. Nobody cares about it. Nobody cares. We can click it. We can see what it is. So I think this is saying, what's it saying? I don't know. Let me go back to the rule verification. Pad R1 on top layer and track something. Top overlay. Pad R1. Where's pad R1? Oh, it's right here. Yes. Yeah, so it's saying, so underneath the resistor, there's little, this is just built into the part. We didn't even make this. This is part of the part. There's little silk screen in the resistor to show you what orientation the resistors are in. This is important. If you have like a whole bunch of resistors that are really tight, sometimes you can't tell. If you have like 2 resistors next to each other, you can't tell if they're supposed to be like this or like this. So they have these little silk screens that show you what direction the resistors need to go. And it's saying that basically it's violating this clearance rule, so that this is too close to the exposed copper. And what's going to happen is if a silk rule violation, none of these matter. Because a silk rule violation is if the silk violates the silk rule and the screen printer is off a little bit, it's just gonna shave a little bit off of the edge of the silk screen. It's not that big of a deal. I never care about silk clearance rule violations. I just don't care. So I consider this a pass. So you typically, typically if we have silk to solder mask, silk to silk, nobody cares. Even minimum solder mask sliver, sometimes this doesn't matter either. So these ones I don't care too much about. Net antenna, when you get to higher frequency circuits, that can matter. Height constraint, I don't care too much about. Silk, I don't know what that one is. But this stuff up here is the critical stuff. The silk stuff, yeah, nobody cares. So I consider this a pass. So for now, I'm calling it a pass. Everything's looking good. We've routed this well so far. If you're following along at home, hopefully you have something that looks similar to this. Don't copy mine exactly though. Do what you want, right? Mine's not perfect. Mine, I left a lot of stuff off. The biggest thing I want you to take away from this is, and a lot of this you'll get better as you go along. You'll realize it's kind of an art form. Just note what you're doing. And if you mess up, there's a couple ways to fix it. For instance, I don't really like where this is right now. I kind of maybe want to move it. So one thing you can do is you can click apart and right click it and go component actions, unroute component. And that will remove any routing that was routed to that component. And so now if I don't like this, if I don't like where it was and I want to move it down, I can move it down, I can take these and move it down with it, and then I can reroute this component. So I can just really quickly go back and route this component. And I want to, oops. Oops. So I'm just hitting tab, changing the preferences, going back to the fat one. There we go. Okay, all right. So that's good. So now we can follow our power path. Now I think that's all good. I was able to move it. We can, save all, tools, design rule check, run design rule check. Still, none of the bad ones. We have the same 16 silk screen. Okay, now, and I like to sanity check it. I like to follow my power. I say power comes in from USB. It gets decoupled through the cap. It's going through this. Maybe that could be a little fatter. Double click it. Maybe let's just bump it up a little. 12 mil. Now I don't like what that did. So I'm gonna. It's all going off the rails now. Okay. Yeah. All right. So current comes in through here. It gets decoupled by this decoupling capacitor. That just smooths it out. So if this 5 volts is a little jittery, it just smooths it out. And also when this thing draws current, it gives it a nice constant 5 volts. So that the sporadic current draws from this are not going to drop this bus voltage because it's got a capacitor to store a little energy there. And then current flows out to the battery. And then current flows from the battery back to the USB. We're good. So this all looks good. Save all. Okay, so next time, so we kind of went through some of the basics. Next time we're going to do more circuit development, more routing, more examples. Follow along at home. I will see you next time.